Hi, today I'll use physics to design the ultimate Pachinko machine. First and most importantly, I'll be testing the air resistance. Initially, the ball will start 48 centimeters off the ground. However, at the end, it'll be only 35 centimeters off the ground. From this, we can compare the potential energy due to gravity through the formula mgh, or mass gravity height. The initial potential energy is 0.0098784, and the final is 0.007203 joules. Now from this we can tell the difference is 0.00268 joules. Because energy is equal to force distance, we can tell that 0.00268 is equal to force times the distance of 1.378 meters which the ball traveled on the pendulum. From this, we can discern that F is equal to 0.00194 newtons. But how can we model this? Because we know the average drag force, and we know that the drag force equals k times velocity squared, where k is a constant equal to half the air density times the drag coefficient times the surface area of the object, all we need to do is find k. In order to work out the velocity, we must first work out the time the ball spent in the air. Luckily, there's a formula for this. T equals 2 pi root radius over gravity in a pendulum. This is equal to 1.391. The distance is equal to 1.378, so the velocity is distance over time, which is 0.991. Therefore, because we know drag force equals kv squared, we can work out that k is equal to 0.0198. In order to accurately simulate this situation, I must also figure out the coefficient of restitution. How much does an object bounce back in a specific circumstance? The coefficient of restitution is equal to the root of the rebound height over the drop height where a ball had been dropped. On my surface, when I dropped my metal ball, it dropped 50 centimeters and only rebounded 4.5 centimeters. In this situation, E is equal to 0.3, meaning that it will bounce back 9% of the original drop height. Now I can input these values into my simulator in order to accurately model what would happen. It seems like in my simulation the balls land to the side more often than they land in the center. Perhaps I can rig my game so that I always win by making it so you only get points if it lands in the center. That seems like a clever thing to do. When designing my simulation, I had to make sure the ball rebounded at the correct angle. When applicable, I separated the velocity of the ball into I and j components, i.e. j equals q sine of theta and I equals q cosine of theta. This is a representation of some of the maths that would take place inside the simulator. When a force of 9.8 newtons was applied, the spring only expanded 0.5 centimeters. From this we can tell that k is equal to 1960. This means that my spring will be plenty strong enough to propel my 2.1 gram metal ball.